Thanks for having me here. And so yeah, I'm going to talk about actually work I was more involved in. So I've been at University of Chicago for about a year now. Before that, I was at UC Berkeley for 17 years. And a project I ran there called the AMP Lab was a place where Spark and a bunch of things related to Spark came out of. And so I'm going to be talking mostly about that work and about the process of doing that at a university. So I guess first of all, I know you guys are pretty hardcore. I know you've been in classes all day, and then during your dinner, you have to listen to another talk. I apologize for that. And then you're going to go back and do some more work afterwards, so I admire that. And so I guess if you have questions, I've got a ton of slides, but I would rather not get through them all and answer questions and have a discussion. Of course, I don't want you speaking with your mouths full, but other than that, we could do it. So I guess before I start, just a show of hands, how many people have heard of Apache Spark? Most people? Okay, good. All right. So okay, so I may be telling some of you stuff you already know, but again, feel free to ask questions. So one thing I'm sure you know is pretty much every field that anyone is involved in is moving from this regime where it used to be really hard to get data to where it's now become a lot easier to get data. And the hard part really is trying to figure out how to make sense of all the data you're able to get your hands on. And it's the kind of science things that people are studying here. It's all around commerce, social networks, and you name it. A lot of people are talking about this data revolution as being a new way of doing science. And so there's this idea of the fourth paradigm of doing science where over time people went from observation and experiment to doing theoretical techniques. More recently, with the advent of supercomputing, the ability to simulate and model complex systems. And the idea is this ability to collect lots and lots of granular data is yet another way of doing science, and is changing the types of questions we can ask and the types of questions we can answer. So it's a big deal. The software I'm going to be talking about didn't really come out of that scientific background. It really came out of the commercial world. And in particular, a bunch of web companies, realized pretty early on that they were going to be dealing with just huge volumes of data. And they believed that the existing commercial systems, mostly relational databases and things like that, just weren't going to be able to scale to the data volumes that they had, or even if they could, it was going to be too expensive and too restrictive for what they wanted to do, which was basically collect lots and lots of information about people and what those people are doing, and then train machine learning models on them, do prediction based on that, and so on. And so companies, especially Google was in the forefront of this, created a bunch of software in-house that they could use for processing huge amounts of data. The one that's most relevant to this conversation is something called MapReduce, which was basically just a simple way of expressing programs that could run across lots and lots of servers, and basically had the property that as you added servers and storage to the system, you could easily scale out the processing onto those servers and process more data that way. And so a lot of people got used to having access to those types of tools, but the problem is they were locked up in these companies. And so there was a movement to start doing open source versions of these to let people outside of those companies get access to this stuff. And one of the ones that's been most influential and successful is a system called Hadoop that really had two major parts. One was the processing engine, which was basically an open source implementation of this MapReduce paradigm. And the other was the Hadoop file system, which was a scalable way of storing lots and lots of data across, again, with this scale-out architecture of being able to just add disks to a system and have the data spread out there. And what happened was, and it's a little hard for me to see it. Hopefully you can see it. Boy, about 11 or 12 years ago, the initial versions of Hadoop were released. And for a lot of people, this was really their first experience with massively parallel programming, or maybe not even that massive, but the ability to run jobs on groups of servers. And people got pretty excited about that, and it really took off. And what happened was people started trying to use Hadoop for things that it wasn't very good at, that it wasn't originally meant for. And you ended up with this explosion of open source software tools for doing all sorts of things. So what would happen is somebody would say, hey, well, I like Hadoop, but I want to run SQL queries, right? So somebody would build a system that would do that. Or somebody would say, well, I've got graph data, and Hadoop's not very good at working with graphs, and so somebody would build a system for graphs, or for streaming, or for machine learning, or whatever. And so that's what all these different systems that you can see in orange and black on this slide are. Okay? And so you ended up with this really active but really chaotic ecosystem of open source software. And all of those systems listed there were all freely available. You could get the source code, you could run it, you could compile it, run it in your own environment. So while all this was going on, at Berkeley we had a couple things happening. So there was this project called the RAD Lab, started at about the same time Hadoop was gearing up. And the RAD Lab was trying to realize the vision of what people used to call autonomic computing, where you would build complex computing systems that would be able to manage themselves. And so the idea was you'd build sophisticated machine learning models based on the telemetry that was coming off of all the machines in your data center. And then you'd use those models to control the machines in the data center. And this worked in some cases better than it did in some others. But for what's relevant to this story is it had a really interesting effect at Berkeley, which was it got a bunch of machine learning people and a bunch of computer systems people to sit together in the same room and work on stuff. And we had 5 years of intensive collaboration across this boundary, which still exists in a lot of places. It's not quite as high a wall as it used to be. But we had machine learning people who could speak systems and systems people who could speak machine learning. And what happened is the machine learning people in that project were trying to do some things with Hadoop. It wasn't working very well. And they spoke to the system students, and they said, hey, can you help me debug my Hadoop program? What am I doing wrong? And the students looked at what they were doing and said, oh, you're not really doing anything wrong. The kinds of models that you're trying to create and the training you're trying to do is just not a very good use case for Hadoop. And they started thinking about what a system that could run those types of calculations would look like. And we developed this thing called Spark. So at the end of the RAD Lab project, this Spark system started bubbling up. And as the RAD Lab was winding down, a bunch of us looked at it and said, well, geez, there's this thing happening with everyone getting more and more data. I don't know if it was actually called big data at the time, but you could see it happening if you talk to anybody in industry. And we said, hey, let's take this group of people we have, the machine learning and the systems people, but instead of kind of the machine learning people working for the systems people, which is kind of how the RAD Lab worked, let's flip it. And let's have the systems work be done in service of machine learning. And we'd use Spark as the basis of that. So we created this thing called the AMP Lab to do that. And both of these projects were set up as kind of time-limited projects. So RAD Lab was 5 years. AMP Lab was supposed to be 5 years, but a year into it, we got a 5-year expeditions grant from NSF, so we made it 6 years. But, and now there's a new project that they're doing without me called RISE Lab, which I can talk about later if you're interested. But that's kind of the context. So, AMP Lab, the idea was, okay, what do we need to do to make sense of big data, right? So how do we make sense at scale? And the idea, and where the name comes from, is that you have 3 basic resources that you can use to make sense of data. The A is for algorithms. So, right, you can think about machine learning algorithms, business intelligence, types of processing, and so on. That's algorithms. Machines was the idea of scale-out computing, either as clusters or in the cloud. And the P in AMP, which I'm probably not going to talk too much about today, was people. And so understanding human-in-the-loop analytics and how they fit in to handle the parts of the problems that the algorithms and the machines aren't quite up to doing yet. Okay, and our goal and our vision was to build a system that would integrate these three very different types of resources. And what we ended up doing was building this entire software stack. It's called the Berkeley Data Analytics Stack. It's abbreviated BDAS, and for those in the know, it's pronounced badass. And it basically, has all these layers. And if you read it from the bottom up, there was a system that came to be called Mesos, which does cluster virtualization. So the idea is you got a bunch of physical machines, and you want to chop them up into individual clusters virtually, so that people can run lots of different kinds of jobs in the same data center. On top of that, we had some storage processing. So Alluxio is something that, that's good, I can't even remember what it used to be called now. Nexus, I think it was called. Or was that, anyway, it doesn't matter. Alluxio was a distributed memory interface that you could put across a cluster. Succinct is a set of routines for allowing you to do search and retrieval on compressed data without having to decompress it. And then on top of that, we built processing engines. Spark, I'm going to talk about in some more detail. That was our version of MapReduce that could do certain types of processing faster than Hadoop MapReduce could do. And something I probably won't talk about today, but is actually a still active project called Clipper, which is meant for, if you think about Spark as being a great tool for training machine learning models, Clipper is meant for once you have models trained, how do you deploy them in an application? So that's what's happening at that level. And then above that is what I really want to spend most of my time talking about, is the set of interfaces you have for getting at the data, whether it's through database queries or through a graph interface or a streaming interface or whatever. And the thing to keep in mind here is that kind of each one of these little boxes was somebody's PhD thesis, right? So this was done at a university as a research project. And so just some numbers. One really cool thing about AmpLab was that we got about half our funding from the government and the other half from companies. So over the course of 6 years, we had 40 companies participate in the project, including our main sponsors who were Google, IBM, SAP, and Amazon Web Services, and then a bunch of others. We got a lot of attention. That's just one number, a couple million visits to our webpage. It was a research project, so we generated, in addition to all the software I showed you, we generated hundreds of papers in really, all the places you'd want to publish in machine learning, in systems, in databases, and so on. We've granted over 40 PhDs from that group of people. And a bunch of these people, as you'd imagine, get sucked up into companies, but a bunch of them are out being professors now at some of the best places. 3 companies that came directly out of the lab and have raised about $250 million in venture funding. And lots of other things that we had nothing to do with, where companies, because it was all open source software, lots of people have taken it and have started companies with it or brought it into their own companies for products. And this is probably the most important one. We've had at least so far 3 marriages have come out of the project so far. Just in terms of reach, I mean, I almost don't have to show this slide anymore since most of you guys have heard about Spark, but it's got a big following. This is a listing of the meetup groups around the world that talk about Spark. So these are people who are crazy like you and are willing to, instead of having a relaxed dinner, go after work and talk about Spark, but there's lots of people willing to do that. And kind of what happened was, when we started that project, we hit this really interesting inflection point, which is it became much more possible for people to have access to really massively scalable processing and storage, right? So it wasn't just the supercomputer centers anymore. It wasn't just the NSA and a few big banks, but massive processing had gotten democratized. In particular, because of the cloud services, it became pay-as-you-go. So you don't have to provision a huge data center to run a big job. You just need a credit card. You can rent the processing and storage you need, and then when you don't need it anymore, you don't have to pay for it. It's a huge change. At the data level, a a lot of the software that, that was up there, it wasn't based on the old data model, the old database approach of, create a schema that tells me what every single piece of data you're going to collect looks like and how it's related. But instead, it was suck in all the data and then try to impose structure on it afterwards, which really made things go a lot faster and made things a lot messier. The ability to do search and query and machine learning and analytics all in the same platform. The fact that people even wanted to do machine learning was something that's been bubbling up. I mentioned, the fact that human-in-loop analytics. And then finally, and I think probably kind of the most revolutionary part, was the fact that all of this stuff was happening, not just in our lab, but really across the world. All of this stuff was happening in the open source. So this really cranked up the pace of innovation, the pace of adoption, and so on. Okay? So all these things coming together kind of led to a really fun and I think really successful academic research project. So here's the basic idea. If you remember that picture I showed you with all, the starting with Hadoop and then this explosion of all these incompatible and varied open source systems, basically what was happening was that people were trying to specialize this idea of MapReduce to solve their particular problem. And what we realized in our project was, well, instead of specializing MapReduce, right, making it, oh, I've got MapReduce for graphs, or I've got MapReduce for text data, or whatever, let's just generalize MapReduce. Let's take this MapReduce paradigm and make it bigger, make it wider, make it more powerful. So that's what we did. And basically, we extended the programming model, right? So you don't just have map and reduce. And we solved this performance problem that was keeping Hadoop from being performant in a bunch of machine learning applications. And I'll show you a little bit more about that. But just these two changes let us build the substrate, Spark, which we could then plug in all those other things I showed you, the SQL and the streaming and the graphs and the machine learning and so on. Okay? So that was really, I think, what separated our particular project from a lot of the other big data stuff that was going on at that time. Okay? And especially because of this data sharing thing, we were able to show pretty significant speed ups for a lot of important applications on Hadoop data. So the great thing about Spark was because we were lazy, we didn't mess with the storage engine at first. And so the original versions of Spark would just, you could take your HDFS files, right, the ones you were using to run Hadoop MapReduce on, and you could just instead run Spark over them. And in a lot of applications, people were seeing 10x, 100x types of speed ups without having to move any data around. And so that's kind of what allowed it to catch on quickly. So in terms of generalizing it, this is what I mean. Instead of just map and reduce, you have a whole bunch of operators, right? And a lot of these, if you're a database person, like I am, kind of make you feel good. Like there's sorts and unions and joins and left outer joins and right outer joins and folding and all these other things that you want to do to sets of data, right? So, and when we went to do graph processing, we realized that some of these weren't sufficient, so we added a few more. And as we added use cases, we extended the underlying platform. So, that's what I mean by making it more general. In terms of this data sharing thing, let me show you kind of what things look like with Hadoop MapReduce. So the idea was, you had some training data and you wanted to build a model on it. And so what you would do in Hadoop is you would read everything in. It would, you'd read it in from, Hadoop was built for systems where you had the storage and the processing and the memory. It's called a shared nothing architecture, all in the same, kind of unit. And so you read stuff in from disk. You'd apply your maps, you'd move things around the network, you'd apply the reductions, and then you'd write out the answer, okay? Now, a lot of the machine learning algorithms that we were trying to get to run well don't stop there. What they do is they say, okay, great, now let me iterate, right? So you do something like logistic regression or gradient descent, where you're constantly, going over the data again and again until you converge on a good answer. Well, what Hadoop MapReduce did in that case is said, okay, cool. I'll read it in again. I'll apply my map functions. I'll move the data around the network again. I'll do my reductions, and then I'll write the answer out again, and so on. Okay, and this is what stock Hadoop MapReduce would do. And so, you're reading the same data over and over again. Sorry, an animation. You're saving the data in between each of those iterations. And it's just, you're basically communicating in your program through the disk, which is, it's hard to think of a slower way to communicate between parts of a program. So really, what we said is, OK, what we want to do is read the data into memory and then remember that we've read it in there. And then, not have to communicate from stage to stage through the disk. OK, so read stuff in memory, let all the program know what's in memory and where it is, and then run that way. And when you do that, that's where you get these kind of speed-ups over the original Hadoop MapReduce. Now, you might say, OK, but that seems pretty simple. And at the level I just showed it is. It's just that there was a reason why Hadoop was doing everything like that through the disk. And it was because Hadoop was designed for a really interesting and challenging environment, where the idea was you would have hundreds or maybe even thousands of individual servers that were sort of not managed necessarily. They were heterogeneous. They were all of different ages and different generations. And you would be trying to run this long-running analytics over this chaotic set of servers. And with high probability, during your execution, 1 or 2 or 3 or even more of those servers would die. Okay? And so Hadoop was designed to be fault tolerant to the presence of partial failures. So as individual machines are going down in your cluster, the computation keeps going, and you recover the parts you need to, and so on. And so to do that, things were written to the disk and then read back from the disk. So if we wanted to play this trick of doing as much as we possibly could in memory, we had to solve the fault tolerance problem. And so that was done through this concept of RDDs, or resilient distributed data sets. And the interesting thing about RDDs is that they're immutable. So what that means is you can't change them, right? So one of my favorite paper titles of all time is Immutability Changes Everything. And it's true. So by making these things immutable, it made the management and the bookkeeping you had to do really, really efficient. Okay? And so, for example, here's a snippet of code on an RDD where you're basically, boy, I haven't looked at this in a while. You're reading a text file, probably from HDFS. You're running a filter over it to pull out, in this case, lines that have the word error in it. And then you're applying a map function to pull out some of the data from the lines that are error messages. Okay? And then you're stuffing that in a final RDD. Okay? Now, in terms of fault tolerance, that looks like this. Okay? So read from HDFS, run my filter, run my map function. And that becomes basically a logical log for how you've created every piece of data that exists at any point in your computation. So you basically use this framework for tracking the lineage of the computation. You know you keep track of where the pieces are and where the replicas are. And then if any machine fails, you can very quickly figure out how to recreate the data that you might have lost. Okay, so that's kind of it. And it becomes possible to do efficiently because of the immutability. You don't have to worry about, hey, for this, for this RDD here, did part of it get updated and part of it didn't get updated? Either it's there or it's not. Okay, so it becomes very easy. So that was kind of the big conceptual breakthrough of Spark. Now, it turns out people didn't like necessarily writing that type of DataFrame code, so we started building more interfaces. So there's an interface that was inspired by statistical languages like R and pandas, where you have an abstraction of a data frame, which is basically a table of data, and then you can run this kind of more imperative type of statement over it, right? So this is joining departments and employees, which is kind of the standard relational database query that you learn, when you're first learning SQL. And you can also write SQL, but some people think this is better. I'm a database guy, I like SQL better, but that's one of the interfaces. Now, what's cool is even though we had this imperative language, we kept kind of this database mindset where you treat you treat this which looks like a program telling you to do this and do this, then do that. But you treat it as a logical specification of what you want, not an actual recipe of how to do it. And so then you can take that statement, you can compile it into some internal representation, and then you can optimize that so that you can change the order of operations, you can pick which operations are going to be most efficient based on what you think the data looks like, and so on, and then run it. And so we built this thing called the Catalyst Optimizer. And one of the cool things about Catalyst is it's a rule-based optimizer where, since it's open source, the community gets to add the rules. So it's the only query optimizer that I'm aware of that's got thousands of people constantly adding to it. And it's getting smarter and smarter every day because of that. Now, what's interesting is you could write straight RDD code with Python or with Scala, which is the language that Spark was originally written in. If you use SQL, there's some accelerated operations that you get to use, so things run faster. But what's really interesting is this, that you can use the DataFrame interface with R, you can use the DataFrame interface with Python, you can use it with Scala, and you get basically the same performance no matter which language you use. And it's exactly because you take whatever it is, you compile it into that internal representation, and then that's what you optimize and that's what you run. So you're actually, at the end of the day, running pretty much the same program no matter which language you wrote it in, which is also a nice feature. All right, cool. Couple other things about Spark, and then I'll wrap up. One of the things people are very excited about now in the analytics world is what they call real-time processing, but basically, processing data as it's coming in as opposed to storing it and then processing it in a batch. A lot of the open source world had adopted this thing called the Lambda architecture, where you basically keep your Hadoop or your Spark or whatever, you take data that comes in, you store it, then you process it, and then when queries come in, you answer the queries against what you've processed. And then they bolted onto the side of that this real-time approach. So as the data comes in, you kind of fork it. You go one through the batch layer, and then it can also go through this speed layer. And when you ask a query, the system's supposed to stitch the old answers together with the new answers to give you kind of the most recent answer. So this is called the Lambda architecture. And it turns out it's really hard to do, right? Because this system and this system were built by completely different people. They weren't meant to work together. They're changing at different rates and so on. And so what we did in Spark is we said, OK, let's not do that. Let's just take this RDD abstraction and make it run really fast. So take the incoming stream, split it into mini RDDs, and then run the RDD program on each of those little batches. So this is called Microbatch. And there's a way of kind of stitching some together so you can get this kind of windowed operation. But it's basically the same code that you would run against in the batch system. It's just running in this Microbatch way that gives you the illusion of real-time processing or close to real-time processing. Now, what that lets you do is, here's a program that basically is reading a log file in JSON, and then it's doing a calculation of what's it doing. It's counting, per every hour, how many times each action shows up in this log. Okay, and so the idea, if you're doing this in a batch mode, you'd read the file, you'd run this query, and then you'd get an output of, during this hour, this operation happened this many times, this operation happened this many times, this operation happened this many times. Now, what if you wanted to process that as the data was coming in? Well, in Spark, what you can do is this. You write this program, and you can see it's identical to the other program, except instead of reading a file, you use this read stream operator. And instead of writing out to a file, you use this write stream operator. But the logic and all is the same. So that's what streaming in Spark was meant to do. And so when you put it all together, what that lets you do is basically, I can take a file, like a JSON file. I can run SQL on it. OK, that gives me a data frame. I can then use my machine learning algorithms to train a model based on the data that's in that data frame. That's what this part is doing. And then once I have that model, I can put it in the processing line of a stream so that I can process the stream, with that model to do real-time predictions. Okay, and this is all, you would write this in one file in one, using all these different modalities. Okay, so that's kind of what the real power, I think, of the Spark environment lets you do. So, okay, so do people care about that? So just quickly, we did a survey last year. This is actually Databricks, which is the company that spun out from the lab to kind of manage Spark. And first of all, they found out it was used in a lot of different places. I saw some of you guys when I peeked in the classroom were doing visualization. This visualization really embarrasses me. Can you see what's wrong with this visualization? It's really, I got to get it fixed. But basically, what they did is the diameter. Yeah, not right. So, so 25 is like 1,000,000 times bigger than 7. But okay, take that. The point is it gets used for a lot of things. Interestingly, this one's a little better. People use a bunch of different languages like we wanted them to, whether it's Scala or SQL, Python, R, Java, right? They all get used a fair amount. And then, to kind of make that point I was making about, having a unified environment, we asked people, which of these do you use? And tell us however many you use, right? So that's why this doesn't add up to 100%. But, a lot of people use DataFrames, a lot of people use SQL, a lot of people use streaming, and so on. GraphX, which is kind of my baby, doesn't get used that much, but that's okay. And more interestingly, basically 3/4 of the people that answered this survey across all those different use cases use 2 or more components, right? So they're not just doing SQL, they're not just doing machine learning. They're doing at least 2 of those. And 2/3 of the people are using at least 3. So this idea of being able to treat the same data set with lots of different tools seems to have some resonance. Okay, good. So let me wrap up. Oh, well, people care about performance. They care about functionality. They're starting more and more to care about ease of deployment and things like that. So just to wrap up, initially when we started the project, our focus was on performance, right? Can we be 10 times faster than Hadoop MapReduce? Can we be 100 times faster? Make sure we do it without losing any of the fault tolerance. I told you a little about that. But what we found later was that what people were really excited about was this ability to use database queries when they wanted to do that, to treat the data as a graph when they wanted to do that, to run machine learning library stuff when they wanted to do that. I think that was true of, well, whatever. But what we're finding now is a lot of people are excited about streaming, right? This idea of low latency, so as the data is coming in, processing it. And then, not surprisingly, everyone's trying to figure out how to do deep learning in this type of an environment. It's all being done in open source. Innovation is continuing, not just in our project, but really, if you look at Apache as one example, every day there's yet a new project that seems really cool that people are doing. But the challenges of performance and scalability and fault tolerance, we'll always be able to improve those. But I think other challenges are starting to bubble up. And one is this understanding of sort of the entire life cycle from collecting data all the way through the pipeline so that an answer comes out. And then you want to know, is that answer correct? Is it biased in some way I didn't understand? Why did it give me that answer? So understanding all of that. Data curation at the other end, communicating the results, all kind of what people really need to be focusing on now. I like this idea of taking this query optimization paradigm that came originally from the database world and trying to push it into machine learning and other advanced analytics. And so I think there's some interesting things there. And then really this bigger questions around, can we trust the answers that the system's giving us? And do we really understand the privacy implications, the ethical implications of what we're doing? At the end of the day, that's what's going to make this technology work or not work. If people don't trust it, if people feel that the technology is biased in some way that they don't understand, they're not going to use it. So this stuff's really important. So I've been dying to use this joke. So a lot of times when people give talks, they say, you know, I'm the one standing between you and dinner. But actually, you guys are really smart. You guys are the ones standing between me and dinner. But that being said, I came all the way out here, and so if you've got some time and some questions, I'd love to hear them. So, thanks.
Questions for Michael? Okay, we'll break the ice. So is this the last slide that you presented? Is the work that is going to be done? You mentioned at the beginning that the team at Berkeley is continuing. Are they going to focus on those topics?
So they're focused on, I forget what RISE stands for, but they're focused a lot on security and on what they're calling decision making. So trying to give quick answers and then explainable answers. So I think you know, some of this stuff is definitely what they're focused on. The optimization stuff, less so, I think, because I was the main database person there on that project. And I think also the lifecycle stuff isn't getting quite as much attention as it needs to. Yeah.
Thanks.
Yeah, exactly. For those of you who are local, I was trained up the road in Madison with the database guys up there, so that's right.
Thank you.
Yeah.
Hi, I had a question about scalability,
Okay.
I guess, and granularity. So we've done a bit of work with Spark over at the NCSA, but mostly with regards to large data sets and typically numerical data sets. And we found two things. With larger granularity of data, we found diminishing returns in terms of the performance of Spark. And with the larger systems, so larger chips, if we don't have a lot of systems with small chips, but rather larger systems with a few larger systems, we also saw somewhat diminishing returns.
Yeah, interesting. Yeah, so I think, so it's true that, so, you know, Spark started in 2009 and really followed this Hadoop model of, I've got lots of fairly kind of medium-powered servers. And as a result, there wasn't a lot of attention. So the real concern was, you know, how do I run this with, you know, a couple hundred machines, 1,000 machines, so on. And there wasn't a lot of attention paid to what we call single node performance. So it was all based on Scala, which is based on Java, which meant that in general, memory management was pretty slow. And so there's a project that's been going now for a long time, for a couple of years, called Project Tungsten, where they basically moved the JVM's memory object management kind of out of the way. And that's actually one of the reasons why SQL, I'm sorry, I'm pointing at the screen, but SQL, when I showed that graph of SQL running faster than the RDDs, it's because the SQL path ignores or avoids most of the Java object overhead. So there's been a lot of work on that aspect of single node performance. There's been less work on the multi-core aspect of single node performance. And there's definitely people that are looking at that pretty intensively now, because there are a lot of people now that are starting to run fewer, beefier machines. And so, you know, to me, what's really cool about Spark as a project that started in academia was it got this tremendous uptake very, very quickly. And now it's got a lot of momentum. And so now, you know, people in companies and at labs are starting to, you know, basically address these problems. Or these things that the original Spark wasn't necessarily designed for. And because it's all open source, you know, Spark gets better. So yeah, so I guess I have two answers. One is, if you wait a little while, it'll get better. And the other is, if you don't want to wait, then you can fix it, and then it'll get better that way.
Okay, thank you.
Yeah.
Will you be working on any Spark-related projects while you're here in Chicago?
Yeah. So so it's good. So I think the short answer is yes. My role at the University of Chicago is a little different than what I was doing at Berkeley. Whereas part of what I'm doing at Chicago is trying to understand data science kind of more broadly and how that spreads across the university. And so I'm doing, I hate to say it, some more administrative stuff than I was doing before. But really what I want to be doing at research-wise is really, you know, the stuff I have up on this slide. And so in particular, one of the cool things that happened to me when I first showed up at the University of Chicago was I met, you know, people really from across campus who were doing stuff with data. And some of them were, you know, in the physics department, and some of them were, you know, in the, you know, astronomy, and some of them were in biology, and some of them were in social science, and some of them were in humanities. And, you know, to a first approximation, everybody had the same problem, which is, I've got all this data from all these different places, and it doesn't fit together, and I don't understand what's good about it and what's bad about it, and I can't, you know, start figuring out how to make sense of it all. So I think, like some of these, some of these things up here, in particular around data integration and cleaning, is really where I'm going to be spending a lot of my research time, because that seems to be the thing that's really keeping a lot of people from making progress.
Anyone else? One additional question from me. So how do you manage with the open source? Do you still have to have a staff there taking care of all the implementations that the people is providing, or?
Yeah,
because
so
there must be still some kind of control, I guess.
Right. So, so we were really fortunate in a lot of ways. So first of all, the team of students who worked on Spark initially were just kind of off the charts productive, and you know, in their ability to do cool things, but also to make them work. And I cut out some of the slides, but the students, one of the reasons Spark took off is because the students saw what was going on, and they were getting all this inbound interest from companies and mostly companies. And so they said, hey, you know, we're going to build a community. And so I showed that map of like meetup groups, you know, all around the world. Well, the first meetup group was in San Francisco. It was started by our students. And, you know, it started off with 25 people eating pizza, you know, at some startup. And, you know, it grew from there. And we would run programs like the one you guys have here to train people. It wasn't 2 weeks. But we would run like, you know, we'd run these things called AMP Camp, which were like 2 or 3 day training sessions. And so the students were willing to take that on. But the other thing that we were really lucky about is, you know, when we started, big data analytics was really the Wild West. And so, you know, the bar, oh boy, I'm being recorded, right? All right, well, whatever. Like the bar, like we were compared against Hadoop, and Hadoop would break a lot. So the fact that our stuff didn't break more often than Hadoop did was actually okay, right? And it's not that way anymore, right? But at the beginning of all of this, there was kind of a window where student-created code could actually get used in real places, and people using it knew what they were getting into. And so, you know, if it broke, you know, they'd be upset, but it wouldn't like ruin their business or their experiment or whatever. So, so we got lucky that way, but also really, you know, just the fact that the students were really good. So to answer your question in particular, I thought we were going to have to hire a lot of staff people, but it turned out I hired a few key people who knew how to do open source software distribution. So we needed a lot of help with sort of the build environment and the testing environment. But in terms of actually writing the code, it was just about done all by the students. And none of the professors, of course. I mean, it was just the students. Yeah.
Any additional question? No? Well, let's thank our speaker. Thank you so much.
Thank you.